Anyway, so let's get started talking about some chemical thermodynamics. So this is 14. Next one will be 15, which is electrochemistry. That's all we're going to talk about for the rest of the semester. Luckily, we're not going to go into like nuclear chemistry or environmental chemistry. That kind of stuff is, I don't think you really need to. I don't even think that's required for this class. So let's go ahead. Oh, I forgot to plug this in. I'm like trying to click the button. It's not moving. Excuse me. It's going to be okay. I promise. Don't freak out. Okay, so what are thermodynamics? There are three laws in thermodynamics. The first law is this law right here. And you should have already gotten some thermodynamics already back in Gen Chem 1. They called it thermochemistry back then, right? But now we're going to dive deep into the physicality of it, or the physics part of it, right? Uh, and so, let's see, funny thing, it says right there, chapter 5. You actually covered chapter 5 in Gen Chem 1. So yeah, it's called thermochemistry then, right? The biggest thing and the first law that you need to know is that energy cannot be created or destroyed, right? It's the same thing with matter. Matter can't be created or destroyed. And so uh, the total energy of the universe is constant, right? So everything in the universe is constant. The energy can't be destroyed, it can't be created, it just changes forms, right? So that's what it says in the third line. Energy can, however, be converted from one form to another to transfer from a system to its surroundings and vice versa. So that governs everything. It tells you how many moles you need to make one compound with another compound, and you put them together. And then if you have more than one of one other compound, you get excess, or less. You don't get as much of one because you can't just change it. Um, so yes, the first law of thermodynamics is going to be this right here, which is energy cannot be created or destroyed. It has to go somewhere, right? It can be changed, transformed, but it's still there, and it's got to go somewhere. Okay, so that brings us to the definitions of enthalpy and entropy, and I can't stress enough how important it is for you to know the definitions of words, right? Yes, know the definition of words, and and so because it's very difficult to answer any of the questions on the exams if you don't know what these words mean. Okay, and so enthalpy is the heat absorbed by a system during constant pressure process, whereas entropy is a measure of randomness in a system, right? So I like to actually call it disorder. Instead of saying randomness, I like to say disorder. So entropy is a measure of disorder in a system, right? And so nature tends to go towards disorder, right? You have to go through and build something, and that takes energy when you build something, right? Let's say it's a coffee mug. Somebody used the plaster and the ceramic, and made a coffee mug, and that took energy for them to make that. But it took no energy for someone to like just drop it and break it, right? And so now what used to be a coffee mug that was quite ordered, right, is now completely disordered because they dropped it on the floor. And so that is an analogy to show you that nature actually goes towards entropy, or goes um, towards being disordered, right? That's also the reason why you die, right? Right now, your cells and your DNA and your proteins are very organized, right? But as you get older, you don't have as much energy, right? And if you don't have as much energy, you can't maintain that order anymore until you start to go into disorder. Then you die, and then really you don't have any energy left, right? And so that's when you start to decompose, right? And so I mean it's the same thing with cars. Everything happens that way. Everything goes towards this order. It took a lot of time and effort to make a vehicle, but as soon as you drive it, it starts to decompose, right? It starts to lose its appreciation too, right? Lose its value. Um, and so that's the thing I really want you to remember, that entropy is disorder and nature goes towards disorder. Okay, so both of these go into playing what we call a process that is spontaneous, right? And quite literally, what that means is that it's a process that will just happen on its own, right? Like for example, you drop a mug and it destroys itself. That's happening on its own, right? So, uh, or you dying, you slowly dying over 100 years of life. That's a spontaneous process, right? So this is your first question of the day. First question of the day. Which of the following is not true about enthalpy and entropy? Enthalpy is the heat released by a system during a constant pressure process. Entropy is a measure of randomness in the system. Both play a role in determining this process. Processes are just spontaneous, or all of these are true, right? So is the definition of enthalpy incorrect here? Is the definition of entropy incorrect here? Or is this definition of what a spontaneous process is in regards to enthalpy entropy incorrect? Or all of these true? All right, so what is the answer here? Everybody, most people picked A. That is correct. Good job there, right? Because A says enthalpy is heat released. Is that true? Exactly. It is the absorbed. Absorbed, da, 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 right? Okay, so what is a spontaneous process then? I already alluded to this a second ago, right? I already alluded to this a second ago, but we'll talk about it again, which I'm sure you appreciate since a lot of you are trying to study for the test. It's weird to have a class right before the test, right? Is that weird? I didn't set this up. I definitely did not set this up. Anyway, oh, just tell them they can take all their exams in discussion. No, I mean, it's going to be great. Oh no, I don't know if that's no. We should have switched it around where but then you wouldn't pay attention after the test either, so it doesn't matter. Anyway, back to this. What is a spontaneous process? A spontaneous process is something that will proceed without any outside assistance, right? Just like I was talking about dropping the coffee cup, it just destroys itself, it shatters. That's a spontaneous process. Processes are spontaneous in one direction and they're non-spontaneous in the reverse direction. So like I was saying before, you shattered that coffee cup, right? But it's going to take you energy to superglue that thing back together again, right? So the example that they show you here is eggs, right? When you drop the eggs, they shatter, and then you get like, well, how did they not break the yolk on that? That's crazy. Um, anyway, I always break the yolk when I'm making like my over easy eggs, so I'm very interested in their egg cracking abilities. Anyway, so he drops this egg, it cracks open, and that's a spontaneous process because it cracks open on its own, right? But it's definitely not spontaneous to go backwards again, to have the eggs go back into his hand still in intact form, right? And so that's the difference between a non-spontaneous reaction and a spontaneous reaction. So the thing that a lot of students confuse though is that spontaneous doesn't actually mean fast, right? You can have reactions that are fast and slow that are all spontaneous, right? For example, you dying is a very slow reaction, right? Not you personally, but a person dying is a very slow reaction that's happening, but it's still spontaneous, right? But then also like a uh, an explosion, right? That's a spontaneous reaction, but it happens very fast, you know. So you can have spontaneous reactions that are fast and slow. So don't think that spontaneous means fast. It's kind of like that thing where people think that volatile means like it's going to be explosive, but volatile just means that it has a very low boiling point, right? So don't confuse those either. But anyway, next one, don't confuse non-spontaneous with impossible because energy can be used to make some reactions spontaneous that otherwise would not be, right? So this is a big misconception as well. Just because it's non-spontaneous doesn't mean that it's impossible. And this is quite apparent in your body as well because a lot of the reactions in your body, for example, in glycolysis and the TCA cycle, right? They're actually non-spontaneous reactions when you look at them on their own. But the reason why they happen spontaneously, it seems like, is because you have enzymes in your body and in your cells that help you make these reactions more spontaneous, right? And if you didn't have those enzymes available, then you would die, right? Then you would die. Um, so I guess, a good example of that would be an enzyme called CTFR, and it's the enzyme where if a person has cystic fibrosis, they have this protein is actually misfolded because they're missing like a phenylalanine, which is my favorite amino acid, in their enzyme CTFR. And what happens is that this enzyme it catalyzes a reaction that transports chloride in your mucous membranes, right? And so what happens then is that if you don't have this enzyme like available and it's not working correctly, you can't transport chloride in your mucous membranes. And if you don't do that, your mucus gets super thick. and you get these things called biofilms. And cystic fibrosis patients end up dying very early on in life because these biofilms get infected in the hospital with Pseudomonas aeruginosa, right? And there's really no way to fight it off because the Pseudomonas aeruginosa is like inside these biofilms, so it's very hard to fight it off. And then the other thing too is that your immune system goes through and tries to attack the biofilms, but it's so hard to get through this like really thick mucus because there's no chloride transport that when they break through, when they try to get through the biofilms, they literally go through your alveoli, right? Break open your alveoli to try to attack the mucus lining where the biofilms are. And the thing that's crazy about it is that it damages your lung at the same time. And so a lot of times, cystic fibrosis patients will cough up tons of blood. And the reason why they're coughing up tons of blood is because their neutrophils and their macrophages and their immune system are going through and breaking apart their lung alveoli just to get to the infection, right? So um, again, a reaction, right, in which is not spontaneous. The transport of chloride in the mucous membrane, right, becomes spontaneous, right, because of an enzyme called CTFR, right? And if your CTFR doesn't work, right? You can't transport your chloride from your mucous membranes, right? And if that doesn't work, you end up dying from cystic fibrosis. So does that make sense, right? So there's plenty of reactions, and that's just one example that actually uh, has a that's just one example that has like a medical, but there's a gazillion of them in your body. If any one of these enzymes in your body are messed up, you could die from them, right? But the point is that they are normally non-spontaneous reactions, right? But they become spontaneous when they're functioning correctly because of enzymes, right? So don't confuse non-spontaneous with impossible, right? They're definitely possible, especially if you have catalysts present, right? If you have catalysts present. Man, so I was I was listening. So Marla is taking. She's in PhD school right now, and she's taking a statistics class, like a forensic statistics class. Holy crap! That class is boring, and the teacher is not good either. Like she has to listen to her teacher, like on, like she when she they record lectures too at OSU, and so she when she listens to those lectures, she has to put it on 2 times fast because the guy talks so slow, right? And so and it's so boring. And I just got reminded of that because I'm talking to you now, and I think to myself, am I talking too slow? Am I talking too fast? Am I being boring? Some people might think I'm talking a little too fast. So maybe slow me down to zero point 0.5 speed, right? Zero point 0.5. All right. So are you going to change? What happened? Dang it. I was so comfortable sitting over here and I got to get up and see why it's not changing slides. Your Apple ID is being used on a new Mac. What the hell? Okay, whatever. Okay, so, all right, so on the same on the same train, we're still on the same train here, the spontaneity of processes, right? Temperature, right, and pressure can also affect spontaneity, right? And these are examples of how temperature affects spontaneity in ice melting or freezing, right? Yeah, so the temperature affects the spontaneity the same way. But just know though that temperature and pressure does affect spontaneity, and an example of how temperature affects spontaneity is the freezing or melting of ice. Okay, weird picture, weird picture. All right, so here we go. Reversible and irreversible processes. So you could have your surroundings, right, and you can have your system, okay, and the system at a higher temperature, right, can actually transport, right, or transfer, I guess they're calling it, heat from itself to its surroundings, right? And then on the other hand, if you have a high temperature out here in the surroundings, it can transfer heat back into the system, right? So here again, we're going to have surroundings at temperature T, but here we have surroundings at both at temperature T, right? And in one case, the system is transferring heat from itself to its surroundings, or it's going to transfer uh, from the surroundings to the system, right? So a reversible process, and we've talked about reversible processes in the past, right? It's when you have a double arrow going back and forth, right? The system changes so that the system changes so that the system and the surroundings can be returned to the original state by acting in reverse processes, almost like equilibrium, right? And this maximizes work done by the system on its surroundings. Okay, so we're all gonna. So it's like if you had like some cold water and you have some hot water, and you mix it together and it becomes warm water, right? And that's happening because the heat is being transferred between each other of the two systems, so that you can reach this. I mean, I'm not gonna, it's not called equilibrium here, but it's like equilibrium, right? To return to its original state, basically, right? So uh, to continue on, so we have a vacuum here, right? And we have gas. That's cool, right? And uh, the movable partition here, right? And so I guess this is like a car engine or maybe a two-stroke motor or something like that. And so um, if the partition is removed, the gas spontaneously fills the evacuated space. Well, that makes sense, right? Because there's a vacuum over here, and if you pull that away, right? If you pull that out, then the gas fills the space because gases go and fill the volume that they're in, right? Especially if there's a vacuum, it sucks it into the space, right? And so now you have the vacuum that is expanded, right, into the space, okay? And then uh, the thing though is that if you try to put this thing back down, you can't make the gas go back to its normal space, right? This little separation right here. If you put that partition down again, it can't go back to the way it was before. So the only way that you're going to be able to get it to go back to the way before is use this piston here and push the gas, which is called compression, right? Do work to get it back to where it was before. So uh, the irreversible process of gas expansion happens here, right? When you pull this partition out and it expands, right? And if you wanted to make it reversible, what that would mean is then you put down this partition and then it goes back to the way it was before over here. But you can't do that, right? Because the gas is already expanded to the entire vessel, and so there's really no way to get it back to the way it was before, where the gas was only on one side. The only way, right, is to do some work, right? And that work is to use this piston right here, and to push this piston, and so that it compresses the gas. And then once you do that, it will go back to the gas will go back to its normal state, right? So the work done on the system here, because you're doing compression, is greater than zero, right? So notice that all you did here was you pulled out the thing and it expanded, and so that's why the work done in the system is equal to zero, because you really didn't do any work. The vacuum made it so that the gas is suspended, but the gas would do that anyway, even if there wasn't a vacuum, because gases uh, do that anyway. Gases fill the space that they're in, right? And so notice how here no work is done for the gases to expand, and it's irreversible, right? Because if you want to do no work, really no work is just putting this back into place, and that doesn't actually do anything because the gas is still on both sides. So what you have to do is do some work, which is now greater than zero, which is push this piston so that you can compress the gas back into its original space, and then you have the pressure the same again, right? So an irreversible process cannot be undone by exactly reversing the change to the system, right? And so in this case, doing exactly reversing the change to the system would be putting this partition back down, right? Or it cannot have the process followed exactly followed in reverse, right? Well, that means pushing this partition down, and then it automatically goes back, right? So what you have to do is do the work, right? So also any spontaneous process is irreversible, okay? Any spontaneous process is irreversible. Okay, there we go. So, which of the following is spontaneous? Which of the following about spontaneous processes is not true? Okay, processes that are spontaneous, sorry, processes that are spontaneous in one direction are non-spontaneous in the reverse direction, right? There are only fast reactions that are spontaneous. Energy can be used to make some reactions spontaneous that are otherwise not be spontaneous, or all of these are true. All right, so what do we think the answer to this one is? Which is not true? Say it again. B, yes. Right. There are only fast reactions that are spontaneous. That's definitely not true. You can have fast and slow reactions. like you dying, right? That definitely happens pretty slowly. I guess unless you get shot or something, right? Or poisoned. Okay. So let's jump into just really, just some very rudimentary stuff, right, about entropy. Okay. Remember that entropy is a measure of randomness in the in a system, right? And so the state function, right, which is just the state of the system, right, is delta S equals the entropy final minus the initial entropy, right? So what you'll see here, right, is that delta S is what we use to signify entropy in like an equation, okay? And so you've actually seen this before, right? Does anybody remember what it means to have a negative delta S? You've seen this before. It's okay. We'll get to it in a second. All right. No worry. I mean, we've seen it before. Remember, we talked about this at the very beginning of the semester. Delta G. Huh? Yes, exactly. So we talked about this before with delta H, delta S, and delta G. Remember that, right? Do you remember us talking about that? Okay, I just want to make sure you guys are familiar with the terms before we get into it, okay? Because we have talked about this before, right? So delta S is, like I said, the entropy final minus the entropy initial, right? So it can be found by the heat transfer from the surroundings at a given temperature, right? Right? So this is what I really want you to see right here, right? So this is the second law of thermodynamics, and it says that entropy of a unit of the entropy of the universe increases in any spontaneous process. It's what I said before, right? Everything in the nature wants to go towards spontaneity, right? And so this results in the following relationships. If you have a reversible process, right, the uh, the, the delta S of the universe is the delta S of the system plus the delta S of the surroundings, and that equals to zero, right? But if you have an irreversible process, delta S, right? Delta S is equal to the same thing again, but this time it's greater than zero. So if you have a delta S that's irreversible, right? It's going to have a number greater than zero, right? So we can relate that to all the other things that we talk about in a second: delta S, delta G, and delta H. Okay. Please change. Don't make me get up. There we go. Okay. So here's entropy on a molecular scale, right? You have the two molecules are colored right here, right? The red and blue molecules, so you need to keep track of them, right? And so the four possible arrangements, these are called the microstates, right? Once the stopcock is opened, right? So there's a vacuum over here, and then you open the stopcock, and then the molecules can do one of four things. They can either go blue and red, one on either side, right? They can stay over here on one side, both of them, or they can go all on one other side, right? Right? And then, or they can go the other way where red is on one side, on the left side, and the blue molecule is on the right side. Okay? So the possible arrangements of these two gas molecules in the double round bottom flask connection right there, once you open the stopcock, those are called microstates, right? So this is entropy at a molecular level, also known as the Boltzmann, right? And so there's going to be this thing later on in life that you're going to be talking about called the Boltzmann constant and the Boltzmann distribution, but you don't have to worry about that now. That's like a PChem thing. Um, and so if you're a biochem major or a chemistry major, you'll have to do the Boltzmann stuff. But that's basically what I want you to know there. So the two molecules start as one side as above. What is the likelihood that they'll end up there at, at each one of these states, right? So these are called microstates because what I wanted to get to was this next slide right here, right? Gases spontaneously expand to a given volume, which is what I said a second ago, right? The most probable arrangement is approximately equal molecules on each side, right? So here we have a gas at 1 atm, right? And we have a flask that's at 0 atm, so that's a vacuum when the stopcock is closed. When the stopcock is open, right, they'll flow across, right? And they'll make it where zero point 0.5 atm is on one side and 0.5 atm is on the other side. Now, this is a spontaneous process, right? But then the non-spontaneous process is this one here, where the gas molecules will move back into flask A, right? That's just not going to happen. So that's a non-spontaneous process, right? Going from B back to 0 again and going back to 1 atm, right? Because the next question is this: which of the following is a spontaneous process? A, where gas is at 1 atm, the stop cock is closed, and you have an evacuated flask, where they're going to go back and forth, and you'll end up with 5.5 atm on both sides, or going back to having 1 atm of gas in A, right? Or if none of these are spontaneous. Thanks. Someone answered D. So the answer to this one here is B, right? The only spontaneous process is when you have them both equal on both sides from the open stopcock, right? And the reason why you know this is the last slide of the presentation is because the next one is this one. So that ends today's lecture. And now I will open up the room the next 15 minutes for questions